Hello, my name is Gerald, and I will be talking about a soft optical sensor and haptic feedback system for remote and robot-assisted palpation. Some background and overview of this work. There is an increasing adoption of minimally invasive surgeries, including robot and remote-assisted palpation. However, in these procedures, the surgeons cannot physically feel the tissue as they are haptically disconnected from the patient. Without being able to manually palpate the tissue, it is difficult for them to detect the presence of tumors. To solve this issue, we have created a soft optical sensor that interfaces with a haptic feedback glove. The sensor contains an array of optical waveguides of two layers. The bottom and top layer are arranged in a lattice with 3D printed indenters that are attached at the intersection of this lattice. The glove itself has microfluidic actuators on its fingertips. When the sensor presses on a tumor, this causes an optical loss in the waveguides. This detection response can trigger the proportional inflation of the glove's actuators. How is the sensor made? We arrange clear optical tubing in a 3D printed mold and pour EcoFlex 50 as cladding. We cure this cladding and then attach 3D printed indenters and secure the sensor to its electronic components to form the completed sensor. For the actuator itself, we pour Moldstar 30 silicone into 3D printed molds. We cure the silicone and we also create a top membrane of Dragonskin 30 silicone. We attach the bottom cladding to the top membrane and then secure this to fabric straps. We validated our optical palpation sensor using a tumor detection test. This was done to assess the sensor's ability to detect tumors at various depths. We made a soft tissue phantom consisting of EcoFlex 10 of Shore 0010 hardness. In this phantom, we embedded SmoothSil 950 silicone tumors. These are of 58 hardness. As the sensor pressed onto the regions with the tumor, the waveguides exhibited an increased optical loss. The bottom waveguides, which are the waveguides closest to the indenters, are more sensitive, and the loss for these waveguides ranged from 4.5 decibel to about 3.2 decibel. The top waveguides, the waveguides in the lattice furthest away from the indenters, showed a loss of about 1.5 to 1 decibel as the tumor depth increases from 2 millimeters to 5 millimeters. In both layers, the loss present when there is a tumor is much higher than the threshold limit. We also performed actuator characterization tests. This was done to assess the behavior of the actuator under various conditions. We first subjected them to incremental changes in input duty cycle. This was done to assess the ability of these actuators to hold distinct pressures in response to changes in optical loss from the sensors, causing different degrees of inflation of the actuators. We reached a max pressure of about 60 kilopascals at full inflation. We also performed some blocked force testing to quantify the force exerted by the actuators upon max inflation. We discerned that these actuators exerted a maximum force about 1.6 newton. We also performed an in vitro validation. We assessed the sensor and haptic feedback system in a simulated palpation procedure, as you can see. The sensor is attached onto a robot arm and palpates a tissue phantom. It first presses on a region with no tumors, where the actuators are not deployed, and then palpates a region with tumors. This causes the loss to exceed beyond a threshold and then causes the actuators to deploy, thereby providing haptic feedback. Overall, some conclusions and future work. The objective of our work was to restore tactile perception at the surgeon's fingertips during remote and robot-assisted palpation. To do so, we developed a comprehensive haptic feedback system that contains an optical palpation sensor and a pneumatic haptic feedback glove. In future works, we would like to test the palpation sensor with tumors of varying hardness. We currently only test the sensor with a tumor of 58 hardness. Another thing we would like to do is to improve the spatial resolution of the sensors. We would like to incorporate denser waveguide arrays and more indenters, thereby having more detection points and better tumor localization for the sensor. Lastly, I'd like to acknowledge the Material Robotics Lab at Boston University, as well as my PI, Dr. Sheila Russo. Thank you.